In the previous session, we discussed the thermodynamic processes that were associated with constant pressure, volume, temperature, and no heat flow. These represent the individual steps that can appear in a thermodynamic cycle. A thermodynamic cycle is a closed path on a pressure-volume diagram in which the system is taken through changes, these processes we talked about, for the purpose of extracting work from heat and maximizing that process. And we call this a heat engine because to extract work or to get work out of a system from the use of heat is our purpose. Now, the shape of the pressure-volume cycle is dependent upon what processes appear in that cycle. Here we have a typical closed path pressure-volume diagram. Notice that in this path we plot pressure as a function of volume, and we have 4 points. Point 1 to number 1 to 2 is one process. Looking at that diagram, can you tell me what is the process from step 1 to step 2? Which one of our iso terms or adiabatic terms is that? Well, as you notice, the volume stays constant. That's a vertical line. So that's an isometric process from step 1 to step 2. Now we know that if the volume stays fixed, there are certain consequences to that on the first law of thermodynamics. If the volume is constant or fixed, then the gas is not doing any work, or there's no work being done on the gas. So what we see here is the pressure is rising while the volume stays fixed. Well, you recall we did sort of an example like that where we fixed the piston in place and added heat to it, which caused the pressure to increase and temperature to increase as the volume stayed fixed. So this, from step 1 to 2, we see in order for this to happen, we have to have heat flowing into our system. Okay. Now, step 2 to 3 is a step. It looks somewhat like a gentle sloping line. It probably has the shape of an isotherm, right? And like down here where we say an isotherm is one of the processes we're going to use in our what's known as a Carnot cycle. But this is not a Carnot cycle. This is just a representative cycle that we're talking about here. But at any rate, notice that going from 2 to 3, we see the pressure is dropping and the volume is increasing. So the gas is pushing outward and the pressure is dropping while it does that. And so perhaps that's an isothermal step where the temperature stays constant as the gas proceeds from state 2 to state 3. And work is being done by the gas. So in other words, the gas is losing energy because it is giving that energy up to do work on something external. Okay? Now, step 3 to 4, notice once again, it's isometric at constant volume. We have a depressurization going on. In other words, the pressure is dropping. And in order for that to occur, heat must flow out of the system as energy is taken away and the pressure decreases. Okay? That means the temperature must be dropping because we've got the volume fixed, the pressure dropping, and therefore the temperature has to drop correspondingly. finally back, remember this is a cycle, so a cycle means we have to return to our starting point, so we have to go from step 4 now, back to step 1 to complete the cycle. That means we are repressurizing, volume is decreasing, and the temperature, again, it looks sort of gentle, increasing, sloping line, so it looks like a isothermal, a constant temperature contraction while the volume goes up correspondingly. Again, that would be a Boyle's law relationship. So that's any thermodynamic cycle is one that takes you around through several processes and returns you back to where you started. And the fundamental question would be for a thermodynamic cycle is, how much work can I get out of this system for the heat energy that I put in versus that which I throw away? Notice we're putting the heat energy in from step 1 to 2. We're throwing it away from 3 to 4. So the difference between those two terms, heat in minus heat out, is going to represent the amount of work that we extract from this heat engine. Of course, our goal would be to build heat engines that have the highest amount of work per heat put in that we can attain. That is, of course, a measure of efficiency. It turns out that the most efficient engine that could be devised was devised by Sadi Carnot, and it bears the name of the Carnot Cycle. And the Carnot Cycle consists of 2 adiabats, 2 legs of the cycle that have no heat flow in or out, and then 2 isothermal legs, okay, in which the temperature stays constant. We will look at the Carnot cycle because it represents the theoretical maximum in efficiency, the best engine you could build to operate between 2 temperatures, the hot and cold temperatures of your system. And then any real engine built operating between those 2 temperatures would have an efficiency not equal or less than that of the Carnot cycle. So the Carnot is our sort of our ideal system, again, representing the best we can do. But if you think about the simplest heat engine, you can have here we have a pressure volume diagram. We can have 2 isometric processes occurring and 2 isobaric, pardon me. Now, let's look at this. This point here is point 1. Notice it's pressure 1, volume 1. Therefore, given that information, we could calculate the temperature at this point, T1, from the ideal gas law. Now, we want to pressurize this gas, okay? We want to pressurize it, increase its pressure, and fix its volume. In order to do that, we're going to have to add heat to it. Heat will flow in from leg A to B. Now, will the gas do any work? Well, there's no change in volume, so it can't do any work. Vertical line has no area underneath it. That is a representation of how we can calculate work by looking at the area underneath the line on a pressure volume diagram. So for a vertical line, there's no area underneath that line, therefore there's no work corresponding to that change. Now, once we get to point B, knowing the pressure at B and the volume correspondingly, we can find the temperature. And we can transition from B to C. And notice that as we go from volume 1 at point B to volume 2 at point C, there is an area underneath that line BC. That area goes all the way from the line BC, sweeps down to the axis volume V equals 0 axis. And that area represents the work done in going from point B to point C. In other words, it's all of the area, not only the shaded area, but the area below the line AD. So imagine a rectangle whose height is the pressure P2, rectangle whose height is P2, and whose base is the difference in volume V1 to V2. So we can graphically calculate area from a PV diagram by looking at the area underneath the line. Now, that expansion of volume from B to C is an outward pushing of the gas, therefore the gas is doing work, therefore the gas is losing part of its energy. Well, in order for that to occur, this constant pressure expansion, we would have to add more heat to the gas, or otherwise its pressure would drop as its volume increased. So from B to C, we see that we have to put more heat in. So we've put heat in to pressurize from A to B. We've put heat in to have the volume expand from B to C. Now we're going to depressurize from C to D. We're going to let heat flow out of the gas. And of course there's no work done in C to D because the volume change is 0. There's no area underneath the line CD. And then finally from the point D to A, we're going to contract in volume. Again, the work is being done on the gas because the volume is going from larger to smaller. So that means there's energy, external agent is doing work on the gas. But at the same time we're extracting heat in order for the pressure, for the volume to drop, okay, at constant pressure. Now the work is the area underneath the line AD down to the axis. Okay? So we have the engine doing work, the gas doing work from line BC, and the gas having work done on it from line DA. And so the difference in those areas, the area under the line BC minus the area under the line DA, represents the shaded area enclosed in the cycle. And that shaded area represents the work done by the engine in taking heat, which is added to it in the first step as well as the second step, and then throwing away heat in the third and fourth steps. So the difference between the heat put in and the heat thrown away represents the work the engine does, and that can be represented by this shaded area enclosed in the cycle. Notice also that we return to where we started, point A here. So if we return to the same pressure, the same volume, then we return to the same temperature. So in any thermodynamics cycle where we return to our starting points, there is no change in internal energy. Delta U is 0. So that is a typical engine cycle shown up here. And we want to take a look at what would be a perfect engine cycle. What's the best we can do? Before we do that, we'll take a look at what's called a four-stroke engine, or the Otto cycle. We have a representation over here of the piston. That is, it's on the bottom side and the cylinder around it with the valve and the spark plug, two valves and spark plug. As the piston pulls downward, the gas mixture flows in, and we have an increase in volume at constant pressure. This is really just setting up the starting point. And then the piston recompresses the gas, essentially at constant temperature from point 2 to 3. The valves are closed. And now we have ignition. Spark plug ignites the compressed fuel-air mixture, and we get a rapid rise in pressure as that piston stays fixed in place. So rapid rise in pressure, rapid rise in temperature. The piston is now pushed outward and downward from point 4 down to point 5, doing work for us. Notice that the volume is increasing, and we're getting work from this source of heat energy. The piston is at its furthest. The exhaust valve opens, and the exhaust gas, which is hot, and there's heat energy in this gas, will now be pressure dropping, and the gas will be pushed back out the exhaust stroke, and once again we start over, and the intake valve opens, and we begin the process again. So that's an Otto cycle. That's a typical 4-stroke engine cycle. And if we were to look at that and figure out the area enclosed in that cycle, we could determine how much work we would get out of that engine as a result of the heat energy we put in and that which we threw away. As I mentioned earlier, Carnot did an analysis of thermodynamic cycles and found that the best engine that could possibly exist, which is a theoretical engine, is one that involves processes of 2 isotherms and 2 adiabatics. It bears his name, and we represent it here. Notice that the 2 isotherms here, where heat is coming into the system and the gas is expanding and doing some work because the volume is increasing, and then the gas continues to expand at constant with no input of heat energy, and then the gas now cools. I'm sorry, the gas doesn't cool, but the gas contracts along the isothermal compressions line and then returns back to its starting point. Notice in these legs we have heat added in the top leg and heat extracted in the bottom leg. We get positive work done during the isothermal expansion as well as the adiabatic expansion, and work done by the gas and then work done on the gas during the isothermal compression and adiabatic compression. Based on the analysis of this cycle, Carnot found that the efficiency of this heat engine could be determined by the difference in the temperature of the hot side, the heat inside, minus the temperature of the heat outside, or the cold side, divided by the hot side. And this number, the efficiency represented by this calculation, represented the best you could do with any heat engine. Any real heat engine built around any other processes that involve these 2 temperatures, the hot temperature TH and the cold temperature TC, would have an efficiency of less than that of the Carnot engine. Carnot examined this cycle by looking at the following information. Since we're going around a cycle, there is no change in internal energy. legs 2 to 3 and 4 to 1 must cancel in terms of internal energy, because recall that there was a temperature change in those legs. Those were the adiabatic legs. The isothermal legs represented zero change in internal energy. So the network ended up being the difference simply between the heat that was put in during the isothermal expansion and the heat that was thrown away in the isothermal contraction. So that represents the work that you get out of this type of an engine. The definition of efficiency, of course, is the work you get out for the energy you put in. Now, for a Carnot cycle and dealing with ideal gases, if you think back to our study of specific heats, you'll recall that Q equaled mc delta T. That was a relationship that showed that the heat energy put in or taken out of a mass m was proportional to the temperature change, so it makes sense that you might imagine that since the difference in the heat put in and the heat thrown away, it could also be proportional to the temperature of those two sides of this process. Then we can calculate the efficiency, which would normally be the work, which is the heat in minus the heat out. That's the work you get from this engine divided by the heat you put in. And if Q is proportional to T, then we can simply write that as the difference between temperature of hot and cold. Or in other words, the efficiency is 1 minus the ratio of the cold temperature to the hot temperature. Remember, those values have to be in Kelvin. If you put 0 Celsius in here, you'd get an engine that's 100% efficient, which is impossible. And since 0 Kelvin is impossible to reach, we can never get an engine that will be 100% efficient. So this is an important calculation because it represents for us the best one could possibly do. If we could build an engine on the basis of the Carnot cycle, this would be the efficiency we would get. In fact, any real engine has an efficiency less than this.